talking about than the proof of Picard's theorem. So we're gonna do that, okay? And then maybe I'll sort of set up a little bit of the background that we need for Picard's theorem, because it turns out that looking at the proof, there's some stuff that I haven't introduced that needs to be introduced. Okay, yeah, and I was also going to do course evaluations today. It seems like some people are skipping because maybe they thought that this isn't going to be on the exam. It's not going to be on the exam. Anyway, so let's start off with this thing that so remember last time we had this thing called Rouché's theorem. Right? And Rouché's theorem basically told you some conditions under which the winding number of the composition of F with gamma was going to be the same as the winding number of the composition of G with gamma. Right? It was that the distance from F to G had to be less than the modulus of G. And in that case, these two compositions would have the same winding. Right? Okay. So what we said was that one of the consequences of Rouché's theorem, and we'll get more than one today, was this thing called what I was calling the n-to-1, the locally n-to-1 lemma. So lemma locally n-to-1. Right. And it turned out that one could get from that to the open mapping theorem, right? And from the open mapping theorem, one could get a proof of the maximum modulus principle. Okay. Right. So this is pretty. You see how central this sort of thing is. Okay. So we didn't give the proof of the n-to-1 lemma, so let's do that. Let's do that now. But are there any questions on like just sort of the general, the big picture at this point? Do you see how things fit together? We just right now we're basically finishing up our our understanding of the behavior of holomorphic functions, and this is it. This is kind of the crucial last bit of it, I'd say, at least in this course. Okay. So let F be a non-constant analytic function. Analytic function at a point Z0. Let G of Z be f of Z minus f of Z0. Right? Of course, G of Z0 is 0. Right? So let n be the order of G at Z. Let n be the order of the zero. As a 0. Okay. Then something amazing happens, right? Then for sufficiently small epsilon, there exists a delta such that for all W in the punctured neighborhood, the punctured delta neighborhood of f of Z0, there are n distinct points in the punctured epsilon ball around Z0 that F maps to W. Okay. So you have this z naught, right? And that gets mapped to some f of z naught. Right? And what this is saying is that for a small enough epsilon here, so for a small enough epsilon here, there is a delta ball around here, so that if you take any point here and you consider the pre-image of that, right? Then that hits. There are n points in here that get mapped to that, right? So this whole neighborhood gets covered n times by the image of this epsilon. I'm sorry, the whole puncture neighborhood gets covered n times by the image of the puncture neighborhood through f.
So it's exactly n points?
Exactly.
Exactly.
Yeah, so it's exactly n to 1. Right? Each point in here gets hit n times.
Okay. So then the whole neighborhood is covered.
Yeah, so the whole neighborhood gets covered. Yeah. Again, I'm not saying that everything in here is mapped inside of here, right? But rather that any point here gets covered n times. So proof of this relies on Rouché's theorem. Say, okay, G has a 0 of order n at z naught. And it's an isolated 0. An isolated 0, right? Because your function is not constant, right? So it's your 0 is isolated. So there exists a neighborhood B2 epsilon 1 star of z naught in which G of z is not 0. So just one first simple thing, right? You know that there's a neighborhood where G of z is not 0. In other words, where f of z is not equal to f of z. Okay. Second thing, second observation. Again, f is not a constant. So f prime is not identically 0. Again, f prime zeros are isolated, so f prime's zeros are isolated. So they exist in epsilon 2 such that in the punctured epsilon 2 ball, twice epsilon 2 ball, f prime z is non-zero. Okay. So now let epsilon be the minimum of epsilon 1 and epsilon 2. So that's we've chosen our epsilon ball. Okay. We've chosen the epsilon. Okay. So now if we look at the boundary of the epsilon ball, this thing is a compact set. So this is compact. So if we look at the modulus of g of z as z ranges over over that boundary, there's going to be you're going to get some infimum, right? You attain some infimum, right? Because you have a continuous function on a compact set. So you actually attain this at some point. Okay. That's what we're going to take. So you think about what that is, right? That's the infimum of f of z minus f of z naught, right? So you're looking at the image of right. If this is f of z naught, you're looking at, if you look at, say, maybe this is f of the boundary, right? And what this is saying is that there's some smallest distance, right? There's some smallest distance delta. Okay, and we'll take that delta will be the delta that we're looking for. Okay. Okay. So pick any w naught in that punctured delta wall around f of z naught. We want to see that w naught gets hit n times. Right? Okay. So we're going to use Rouché's theorem to do it. So observe that on the contour, if you take your z on the contour, of course, g of z is bigger than or equal to delta, right? So you pick any w naught on the inside there, right? And this delta is bigger than the distance of f of w naught to f of z naught. Okay. It's the distance of w naught to f of z naught. Let me write it down. F of z naught to w naught. Okay. Right. G of z, right? G of z is this. This is bigger than delta by construction of delta, right? And delta is this radius here, so it's gonna, if w naught is inside there, then the distance is less than delta. Okay, so now we're going to apply Rouché's theorem. Rouché's theorem says that then the function plus the other function has the same number of zeros as g, right? This was one of the forms of Rouché's theorem, right? If this guy is bigger than that guy, then the sum of the two functions, has the same number of zeros as this thing, right? Okay. As the bigger guy. Okay. So inside in the function ball, right? Right. But how many? So what does that tell you? That tells you that, well, what is this? G of z plus f of z naught minus w naught. Well, that's f of z minus w naught. Because remember what g of z was. G of z is f of z minus f of z naught. Right? F of z minus f of z naught plus f of z naught minus w naught. That's this. Right? So this has the same number of zeros. That's G, right? That's G. But G, right? G had n zeros. Since G had n zeros, this also has n zeros, right? And so f of z equals w naught n times inside there. Okay. So f of z equals 0. F of z equals 0 occurs n times with multiplicity counted. But we also required that, and since G prime is f of z, f is f prime, which is non-zero in our ball, we know these are simple zeros. Okay, so not only do they occur n times, but they occur n times separately. Right? They occur at n distinct points. Okay, so this is the proof of the n-to-1 lemma using Rouché's theorem. Okay, any questions? Yeah, Ellen.
Can you explain the part over there about
Sure. Which part?
now the boundaries compact, so and we give your delta.
Yeah. So we made this ball, right? We made this ball, in which G was non-zero, and in which G prime was non-zero. Okay. Then you look at the boundary of that ball. I mean, in fact, that is true in the double ball. Take the boundary of this ball. Right, and that's a compact set. So you know that since you have a continuous function on a compact set, it's going to attain some minimum value. Right. That minimum value is not 0. That minimum value is away from 0, right? Because you know that your function your function is non-zero in here, and so you can't go down all the way down to 0. Right? So there's going to be some actual minimum value away from 0. Okay. Which part is not clear? So that delta is what we're going to use. Right. So what is this? This is the closest that f of z gets to f of 0. And we use that delta. As the boundary of as the radius of the disk that we want to get. But I feel like I'm not.
No, I'm just now reading what comes right.
Okay. Okay. So you want me to keep on going, or
No,
I can say it?
Okay. Thank you.
Right. So. So you say, okay, let's use that delta as that's the delta we're going to be. Remember, we wanted to find an epsilon and a delta that had this relation, right? So that this delta ball was covered n times, right? This turns out to be it. Let's pick a point and show that it is actually covered n times. So pick anybody in there, and then using Rouché's theorem, we see that in fact that this function has n zeros, right? What does that mean? That f of z hits w naught n times. Okay, and w naught was arbitrary, so whatever w naught we chose, this is gonna happen for any w naught. So every w naught inside there is gonna get hit n times by Rouche's theorem. Yeah.
About the Rouche's theorem.
Yeah.
I understand kind of why this like fulfills the hypotheses, but I get because when I was looking back at Rouche's theorem, right, it's like we're talking about this integral around a curve. What curve are we talking about here?
The boundary.
The boundary.
Right? The boundary of the disk. Okay. Right? So we found this, we created this disk. Inside that disk, we have only g of z equals 0 at the center, but nowhere else, right? But nowhere else. That's what we wanted, right? So that n times exactly n times, right? Exactly n. Right? The same number of zeros as g. We made this ball. We created this ball so that g has no zeros except for the center, where it has a 0 of order n. Okay, and so when you what does Rouche's theorem say? It says that in that disk, because of this relation, g and g plus this are going to have the same number of zeros. So this has the same number of zeros as this guy, right? So this is 0 n times, and which is what you're hoping for. Interesting.
Why was it important that the zeros be simple?
That's the statement that you're trying to show, that there are actually n separate points. That there are n separate points that get mapped to each point in the what's the goal of the lemma? To show that for every point in here, there are n separate points here that get mapped onto it.
Mm-hmm.
That every point here gets hit n times.
But it doesn't matter what order. Well, okay, so a 0 of f of z minus w naught is a point that f of z maps to w naught.
Exactly. Yeah.
So if you already have that there are n of them, I don't understand why you're not done before you say, I'm not sure why you're not done right now.
With multiplicity.
Oh, adding up.
Yeah. So, right, with Rouche's theorem just tells you up to multiplicity, right? So they could be all at the same point, which is not really what you're hoping for, right? Because then there would only be one point. That it's not an n-to-1 mapping, but then what is it? A less than n-to-1 mapping, right? That would be the less than n-to-1 lemma. Okay, but we actually wanted to prove the n-to-1 lemma. Yeah. So you just make this small observation that, well, look, the inside that disk, the derivatives were non-zero everywhere, right? So they actually were simple. But you're right that this is sort of like a small point. The big point is this, right? And then the small thing here makes it that they actually are separate. But that was the easy part, and you didn't need Rouche's for that. Okay. So yeah, so great, right? That's the locally under one lemma. It gives you it gives you these other the open mapping theorem and other things. In other texts, sometimes they start from the n-to-1 lemma and go from it to Rouche's theorem. So there's a way to get it in the opposite direction. But I don't know. I wish I had time to look at it and explain to you. But, okay. So so the way I'm presenting things is sort of like using Rouche's theorem as the big tool to get all these things at the end. But it could just as well be done with this thing as the center.
Is there a global n-to-1 theorem? That even makes sense.
Well, let's think about it, right? I mean, what this says is that at each point you have a different end. Right? At each point you have a different end. So, right, at at each point you look, there's sort of an order of how much you attain that you attain a certain value, right? Right. Here's your function. Right? You evaluate it at a certain point. You look at this other function, f of z minus f z naught. So at any point you do this, right? Of course, z naught is going to be a zero of this to some order, right? And so at every point you have a different order attained, right? And so at every point you have this thing that locally, if you look at the image over here, it's covered n times, but that n changes everywhere. Yeah. Okay. Some other cool things. Hurwitz's theorem. So this is one thing that's called Hurwitz's theorem. I found other things that are called Hurwitz's theorem that are sort of similar but not exactly the same. So another significant consequence of Rouché's theorem. So let f of n from A to C. A is again a domain, be a sequence of analytic functions converging almost uniformly that is converging uniformly on all compact subsets. Or you could just say on all disks, as they do in the book. It's a call. Converging almost uniformly to a analytic function f. Right? You know from Weierstrass's theorem that it's going to be analytic because you have the almost uniform convergence. So this is by Weierstrass's theorem. Just a function f that is not identically zero. Okay, so now something cool happens. Okay, then for any point z naught, f of z naught equals 0 if and only if there exists a sequence z sub n such that z sub n converges to z naught, and such that for some n, fn z sub n equals 0 for all n bigger than equal to n. The cool part is this direction. Whenever you have a 0, there's a sequence of points z sub n for which f sub n z sub n is 0, and those z sub n's converge to your z naught, converge to your 0. Okay. So whenever you have a 0, it's because there's zeros for your sequence, and those zeros creep up on this 0. Okay. Every 0 is a limit of zeros of the f sub n's. That's the only way you can get a 0. If you have zeros for the f sub n's, and they somehow start going somewhere, and they bunch up, and they turn into the 0. So to show you how weird this is, or maybe, to show you how weird this is, here's something to think about. If you consider the sequence of functions f sub j x equals x squared plus 1 over j. Right? So you have these parabolas, right? You have these parabolas, and they're creeping downwards towards the y-axis, right? So it reveals like. Okay. So none of these guys have zeros, but their limit has a 0. Okay. Right. So these converge almost uniformly. To f of x equals x squared, which has a double 0. Okay. So that's different from what Hurwitz's theorem says has to happen for complex functions. Now consider the same functions on the complex plane. Right? Consider the same functions on the complex plane. Again, you have uniform convergence, almost uniform convergence to f of z equals z squared. And if you think about the zeros of this, each of them does have 2 zeros, and those zeros, as j goes to infinity, sort of head towards 0, where they lump together and become the double 0. Right? Each of these has a pair of zeros, and as j goes to infinity, right, then they turn into the 0 there. And that's what Hurwitz's theorem is saying has to happen. Right? The only way you can have a 0 is if your sequence has zeros that, in the limit, tend towards the 0. So, okay. So this will rely on a lemma. Proof of this relies on a lemma, which is a consequence of Rouché's theorem. Again, let S of n be a sequence of analytic functions converging almost uniformly to a function f that is not identically 0. Then, for any simple closed curve gamma inside of A that passes through no zeros of f, there exists a number n. There exists a number n, and it depends on gamma, such that for all n bigger than that n, the number of zeros of n inside gamma equals the number of zeros of n inside gamma. Okay, so this is the lemma, right? You have there's some curve, right? There's some curve gamma that passes through no zeros of f. Then past a certain point, the number of zeros of f sub n inside gamma will be the same as the number of zeros of f inside gamma. Okay, so it's not too hard to show. Here's the proof. Say, well, f modulus of f attains by uniform convergence. There exists an n uniform convergence of f sub n f on gamma. There exists an n such that n bigger than n implies that that this is smaller than n everywhere for all c. Right. You can make the distance between these guys as small as you want. Right. That's what uniform convergence is. Okay. Now that n is smaller than f by construction. Right? That n was the minimum of the modulus, so we know that this is true. Okay. But then, by Rouché's theorem, we're done. Right? Fn and f have, right? Here is the man and here is the dog. Right? These things have the same number of zeros. So that's pretty straightforward. Any questions on it? I should probably not say things are straightforward. This is completely trivial. Does anyone have any questions about this? You know, when I first started teaching, I kept on saying that everything was trivial. Here's this trivial fact, and here's this other trivial fact. And the professors who I was TAing for said, "Stop saying that." Yeah, which was right. You know.
Yeah, I feel like eventually saying something is trivial is just a way of saying I get this.
Yeah.
But wait, that's not what it means then, right?
That's not what it means. I mean, there's actually, I think after, after doing math for a while, now I understand what trivial means. Trivial means that you can do it with a lot of hard work. Right? Right? With a lot of hard work, and basically anybody could do it. But you didn't require some sort of incredible insight. You didn't require some like flash of insight to do it. It just happens if you like. It's something that if you put in a certain amount of work, the result is going to come eventually, right? Whereas something that's non-trivial is, no matter how much work you put in, you may never get it. Right? You may never get it. So there's a story that maybe illustrates what trivial means better than what I'm saying. The mathematician Hardy, probably some of you have heard this before. The mathematician Hardy was giving a lecture, and he said, "Well, it's trivial that this fact follows from this fact follows, blah blah blah." And some students said, "Professor Hardy, is it really trivial?" And Hardy, thinks about it, and then he walks around the room. He walks around the room. And he walks around. He does a circuit in the room, just like walking around the room. And then he leaves. He leaves the classroom. 15 minutes, he comes back in, and he says, "It is trivial." It is trivial. And then he keeps on going. Right. So, you see what I mean?
I don't get it.
Yeah.
Like you want to verify it.
Yeah.
Okay.
So, it's something that it's not trivial in the vernacular sense, right? It's not trivial in the vernacular sense.
I thought it meant you could get there in like one step based on like previous results.
Oh, maybe, but
Corollary.
rather, I think it's more like this business of whether you need the flash or not. You don't need the flash. That seems. Yeah, I think that's. Your trivial is too trivial. Okay, so now let's do the proof of Hurwitz's theorem. Right, this business of zeros have to be limits of zeros of your sequence. So, sort of an odd one. It's kind of cool. Suppose you have a zero. So we'll do the interesting part. Suppose you have a zero, and we'll find the zeros that converge to it. Recall f is not identically zero. So this z naught must be isolated. Right? This must be an isolated zero. Right? I.e., there exists delta such that f of z is non-zero inside this ball, this puncture ball. Okay. So you know it's non-zero inside there, except at the center. Okay, and let's say it's an isolated zero of order m. Now, let gamma z k be the boundary of the ball delta. The ball centered at z naught, but a radius delta over k. Okay. Right. So we have this z naught. Right. There's a delta ball in which there are no other zeros, right? And then we take gamma 1 is going to be the first guy. Gamma 2 is going to be the half ball. Gamma 3 is the third, the fourth. Right? Quarter radius, etc., etc. Okay. So then by the lemma, right? By the lemma, for each gamma sub k, there exists an n sub k, such that for all n bigger than or equal to n sub k, the number of zeros f sub n inside gamma sub k is n. Okay. Right. So for each gamma sub k, right? Here's gamma 1. There's an n sub 1, so that for all numbers bigger than n sub 1, then f sub n has m zeros inside there, right? There's for gamma sub 2, there's an n2, right? And you can take it to be bigger than n1, so that for all n bigger than that, fn has m zeros inside gamma sub 2, right? Okay. So just start. So let n be n sub 1. Let n be n sub 1, and you know that starting from there onwards, then say for n between n sub 1 and n sub 2, we know that the f sub n's all have zeros inside the gamma 1 ball, right? So choose the f sub n all have, in fact, m zeros. Right? You only need one, but they have m zeros inside gamma sub 1, right? And then once you cross n sub 2, you know that you can choose choose one for each, right? F sub n, z sub n lies in is 0, right? Right. So choose z sub n that lie in the gamma 1 ball, right? And then once your n crosses n2, you say, okay, now I'm gonna choose my z's to lie inside the gamma 2 ball. Once you cross M3, you choose your zeros to lie inside the gamma 3 ball, and so on and so forth, right? And so you end up with a sequence of zeros that end up in successively smaller balls, and so that's the construction. Yeah, Christian.
I don't understand why the Fn have. Where is that coming from?
M is the order of the zero.
So that's the order of 1 0. So why do all these f of n's have m zeros?
From the lemma. Remember, the lemma said that that given any simple closed contour, eventually the f sub n's, if they converge uniformly to f, are going to have the same number of zeros as f. Right? F has m zeros inside there. Right? They're all bunched in the center.
Oh, okay.
Okay.
That's the multiplicity then?
Multiplicity.
Okay.
Yeah. Yeah, multiplicity. Yeah, so keep that in mind. Yeah, multiplicity. Whenever we're counting them, we count them with multiplicity.
Okay.
Yeah.
But so for the Fn,
Yeah.
are they not necessarily on top of each other anymore? Is that how it goes?
It does. Yeah, they could be on top of each other, but at least we have one, and that's all we wanted.
Okay.
Right. All we wanted was that for each f sub n, we wanted a time past which everybody has 1 0, and those each of these f sub n's has to have a z sub n where it's 0, and those z sub n's have to converge to the center z naught. Okay. Well, we know that in fact each of these guys has m zeros inside. Past this time they all have m zeros inside this. Past this time they all have m zeros inside this, etc., etc. And so we can construct a sequence of z sub n's so that they're all zeros of the corresponding f sub n's, and they converge to the center. Is that clear? This last part isn't spelled out that clearly. Isn't spelled out in the book, but that's probably how you do it. Okay, any questions about that? Okay. Pretty cool. I hope you think it's pretty cool. Okay, so one last fact. One last consequence. So correlating. Again, we get the situation, almost the same situation before. These are analytic, and they converge almost uniformly to your analytic function f. If f is 1 to 1, if the f sub n are 1 to 1 on A, then either f is 1 to 1 or f is constant. And maybe the way they say it like this, say f is non-constant. Then f is 1 to 1. It's the same thing, of course. So, right, so basically, being 1 to 1, if you have a bunch of 1 to 1 functions, then they're going to converge to a 1 to 1 function. 1 to 1, this is preserved under this almost uniform convergence. So here's the proof. Say f of A equals f of B. So suppose there are 2 points that end up with the same value. We want to see that, want to show that A must equal to B, of course. So let G sub n z be fn z minus fn a. Let G of z be f of z minus f of a. Then G sub n goes to G uniformly, or almost uniformly. Almost uniformly, and G of B is equal to 0. G is not identically 0. So, by Hurwitz's theorem, there exists this sequence Z sub n such that G sub n goes to B, and G sub n, Z sub n equals 0. Okay. But G sub n, Z sub n is F sub n, Z sub n minus F sub n a. Right. And each of those things, each of the F sub n's were one to one. Okay. So that tells you that Z sub n must be A. Right. So they're all equal to A, and they converge to B. So B must be A. So I'm going to stop here, and we'll do course evaluations.